Hi friends, I am Professor Prabhakar V. Varde, and this is a course on risk conscious operations management for complex engineering system, and today's topic is risk based engineering and therein the role of probabilistic approach. Because in previous lecture we discussed deterministic approach, and now probabilistic, because deterministic and probabilistic, these are the two very important modules of risk based engineering, and risk based engineering provides the platform for risk conscious operations management. That is the connection. So let us see how probability or randomness is becoming important even in the advances in science. Okay, because now there is a realization that randomness is inherent part of any engineering or scientific or even societal domain. So if we want to achieve the rather to reach the truth, then probably probabilistic component is very important, because therein we model the probability, and there also we have two kind of epistemic and aleatory. So here what we are talking about the aleatory, and then we have the other component also, which where you can identify why the randomness has come, whether it is model, data, method, environment. So those kind of things are apportioned to the epistemic component of uncertainty. So in classical science, like in PRA also, or in deterministic also, there is a procedure to estimate the point value, like the flow will be this much, and but then if I do the same equation in Monte Carlo simulation, I will get the variability, that is upper bound, lower bound, median value or mean value, and that is a correct realization, because point value may not be, and then we say that okay, we have taken a conservative value, we apply by a factor of safety and take the upper bound. This is the way we have been handling traditionally, but nowadays science is better understood and there are good computational methods. Monte Carlo is a very computational intensive method, so that now we have faster computers, so we can do that. That is no more a limitation. Now you see the example of quantum mechanics. In quantum mechanics, if you take the classical science and advanced science, the quantum mechanics is epitome of modern science. We have come out of the Newtonian science and all, wherein as we go into the details, like from micro to nano to atomic level to structure of electron, proton, neutron, and now this double slit experiment is an eye opener, or is a very important observation. What it says is, it's like wave particle theory. What we say is that if a particle, which is a single particle, either it will pass through one of the slits, okay, and then one is expecting that it will form two bars here, because either it will pass from here or it will pass from here. But the randomness that is associated with this, let's say this source of particle, electron gun, I would say. So when it passes, this kind of pattern is formed. Why this kind of pattern is formed? Because of random behavior and wave particle duality. Why we are telling this? Because sometimes the electron behaves like a wave, and sometimes it behaves like a particle. So this is one thing. Second thing is, it is not possible to deterministically find out the location of an electron in the atom. It is only probability which can tell us that electron will be here or it will be there or somewhere else. So, when now there is a deeper level, there is a relation of probability or randomness, then probably and it is none other than quantum mechanics, which is the future of science, is conforming to this kind of observations. One more observation of this double-slit experiment is, if there is an observer, this wave particle behavior collapses. So, suppose here I have put some partition, so observer is not able to see this phenomena, and that is where the consciousness or the human consciousness comes into the picture. I will show you on the next slide. He is seeing only 2 bar, okay, but when nobody is observing and you are sensing this through detectors, you will find, like we saw in the previous slide, couple of bars, because particle is, you can find any one of these regions as its location for on the target board. Okay. So, having started, the point I was trying to make is probability and randomness is a part and parcel of all our endeavors that we do, and I think quantum mechanics is the best example that can endorse this kind of observation. So, when I see, so and this is more important because we are talking of risk conscious operation management. That means observer effect is there, whether we are observing certain phenomena or we are not observing certain phenomena, the reality collapses actually, and advanced research and all is going on, we will not go into that, but we picked up one is the randomness, other thing is concept of randomness and its behavior, and second thing is consciousness. How and we are assuming in our risk conscious operation management culture that consciousness is fundamental, cognition and all, unless until there is a bias of consciousness, cognition may not be not as a single independent unit. It is being charged by a bias which is called consciousness, and then it manifests into many real time focus, concentration, many things actually. So, having discussed on this randomness or variability, now where the randomness and all comes from, it is parameter randomness, model randomness, or model imperfect model which is not close to reality, it will have its own variability. Human behavior, yes, we can consider it to be a random behavior, okay. Process randomness, external condition, it could be internal, external, assumptions and randomness, data randomness, we know that data has got variability, boundary condition, randomness and these together lead to forms a motivation for probabilistic modeling. And now here we complete the story. So, we induce the risk here. So, we come back to our probabilistic risk assessment. So, there cannot be any better way of starting a lecture on probabilistic risk assessment, starting from randomness, consciousness, and now risk is manifest there. So, it is probabilistic risk assessment. Fine. Come back to our domain. Now, we are talking about the complex engineering systems. So, there are 2 major states, operational state and accident condition. Okay. These operation states are also even sometimes safe shutdown is also low power operation is also considered as a part of operation. Only thing is it is not in accident condition domain. So, other states are all like anticipated transients, many states, they form part of this envelope that is called operation state. Okay. Now, accident conditions. Accident condition, earlier it used to be design basis accident and beyond design basis accident. It was a very recent realization. Okay, beyond design basis accident, there can be scenario, they are called severe accidents, you know. So, and then there could be some anticipated operation extension conditions, design extension conditions, wherein we are not into the design basis accident, but we are somewhere around the threat. I would call this area as threat area, where situation can go either this way or this way. Similarly, we have a design acceleration condition here also, some variability, and plant can enter either this way or this way, that is beyond design basis, and beyond design basis also can enter into the severe accident scenario. So, when you have so much of detailing or so much to do, then one point emerges is we have to bring completeness in understanding of how system behave and how variability can manifest, which would impose upon us infinite scenario. We can handle them in some classes and categories the way we have over here. So, it becomes manageable actually. This is what the range of plant state we are defining, because these are very critical to modeling, because when I develop a PRA model, I develop for normal operation, that is full power operation. Okay, I assume that full power operation is the normal operation, but many plants they operate at 90%, 92%, 93%. We assume that the safety requirement will be the same, because heat production continues, nuclear chain reaction goes on. Similarly, anticipated operational occurrences, what we mean by these states are the condition or transients which have been factored into design of our plants, like class 4 power failure or offsite power failure. It is normally, technically it is called class 4 power failure, and otherwise it is offsite power failure. Offsite power failure, that is power which is coming from grid to our plant. If it fails, and we know that it will fail, so these are factored into our plant design, and it form part of our design basis. And we also factored in design basis condition. But sometimes the situation, because every time something happens, there is a new element. So, beyond design basis also occurs and severe accident also occur. Okay. We have seen at least 2 severe accidents which have gone beyond design basis, and that was Chernobyl and Fukushima in 2011 and Chernobyl in 86, sorry. So these are the complete, you can say complete canvas of plant operating states. Now, okay, this is our central idea in this lecture, role of probabilistic safety assessment in risk-based engineering and in risk-based engineering. Okay. PRA recognizes why it has come, because there is a understanding or acceptance that randomness is inherent part of all our engineering endeavors. Though it is new, because deterministic had been there for a long time. This is new in the sense that last 40 years or 50 years it has developed, and the kind of maturity now we have here, and now we have level 1, level 2, level 3 PRA. Level 1 PRA is system analysis, what goes wrong with the system, that is process system, safety system, modeling. Level 2 is if the hazard has entered into the containment, what will be the containment phenomena. Level 3 is hazard has gone out of the reactor building, and what are the different scenarios. So, level 1, level 2, level 3. But this is true for nuclear industry. But in other industries, we will see so many hazardous gases are installed, there is no containment, or even if there is some provision, there physical provision. But whether they are level 2, level 3, no. Here, if any pressure vessel is leaking, the hazard is right into the atmosphere, and there is a good possibility it can reach the public domain. What happened in Bhopal, of course, it was in long time has passed over there, Bhopal gas tragedy. But yeah, that was a reality. Now we have got more matured, we have provisions and all, and you will see for how popular this approach is. 430 plants are there world over, more than 430 plants are there, and for most of the plants, level 1 PRA exists, level 2 also to some extent, and level 3 PRO people are working on it actually. So, this is a sort of vindication of the recognition that the PRA tools and techniques that have been developed. Its application is concerned, yes, from deterministic we would not have been able to have a lot of applications, but PRA is a very effective method for developing various application like identification of component, prioritization of the component. That is one thing for maintenance management based on probabilistic insight and severity of those things. So now those I would say trivial tools and methods like failure mode and effect analysis, failure mode, effect and criticality analysis, various failure mode family of methods are that are there. Here we have because PRA elegantly carries the human factor, common cause failure, which are the weaker point in safety analysis. So there we have a lot of assumptions, and of course to some extent it takes care of digital system also, because even in software randomness is recognized now. It is not a deterministic process. So when it goes, software goes beyond certain limit in size and volume, it behaves like a random unit, because it depends on input, what input is coming, what output is going, and what are the different modules of the software they are behaving in certain way. So and then security. For security system, PRA has become a ready-made. PRA framework has got so, and now there is a work going on probabilistic security risk assessment. Okay. Now just some illustration to understand the PRA of operating plant. What we are discussing is there is a difference between PRA of a operating plant and PRA of a plant which is being designed. What is the major difference? Major difference is that operating data is not available. So normally the data that is available in the literature, those things are used. Technical specification, because safety analysis is going on, so technical specification may not be available. So we lack on safety acceptance criteria, or failure criteria, or success criteria. So many of the informations are not available, but there is always a way out. Generic source is one thing, then there are similar plants that are there, logic model diagram that we can create, and then brainstorming can indicate external event, internal event. So we can definitely create a list of initiating events. So for operating plant, at least if 10 to 15 years of experience is available, then we are comfortable. And then in operating plant, we have this performance data available, unlike our design basis conditions. Maintenance data is available, which is a big volume of data that form part of the maintainability design and this thing. And then monitoring surveillance insights are available, which are the weaker areas. 10 to 15 years is sufficient to see any pockets where improvements are required. Human performance data, again here also, where human performance adequacy is excellent, is not excellent or good, we can perform, like in nuclear plant, fueling operations, they require huge attention when we are handling a fuel. So, and you will not believe it, thousands of the rods have been done so I have got this thing, and no accident condition. So human can perform sometimes, not sometimes, most of the times exceedingly well, and that's how we call nuclear industry is the safest industry. I mean, we can take credit of it. And then safety criteria and conditions that are available, system thermal hydraulics, because it is being demonstrated, and that is how sometimes the operating plant creating a simulator is much accurate and effective than having for a design plant, because since plant is not operating, there are many things which are having a higher uncertainty associated with this. And then emergency procedures, they are available. So all the documents are available, experience is available, data is available, physics is available. So it becomes easier for developing risk conscious approach for this one. Now deterministic acceptance criteria is one of the thing, and our objective was how deterministic assessment has advanced toward the best estimate approach. And in the best estimate approach, the role of probability we can see here. like we have been, or we will be discussing, but in risk based engineering you will find it 95% bound, upper bound, median value or mean value, and 50%. These are routine things there, and you simulate it using Monte Carlo simulation, and as part of fault tree analysis, as part of event analysis, and then so we have uncertainty range. But you see, industries are very conservative sometimes. So in red I have shown you the old system, deterministic system, which was conservative in the sense that plant has got safety limits. This should not be violated. This is a threat condition to the plant. And what is the gap? Whatever estimates that we have obtained here, so and the safety margin, you can see how huge safety margin we kept here, so that in no situation my plant goes to this state. So this was a basically conservatism built into the, and now probabilistic approach came. So regulators having the acceptance criteria at regulatory level, and then point conservative values, and then finally upper bound and lower bound. But you see, 90, even from 90% bound, acceptance criteria is so much having so much of conservatism built into the system. So it is up to a industry requirement where to operate, but the framework is already available. So traditional approach was deterministic, and best estimate however where uncertainty plays a, and that's why best estimate uncertainty modeling code it is called. Uncertainty evaluation does not form part of the best estimate approach. However, the regulatory stipulation form the acceptance criteria. I think here uncertainty evaluation does form part of the same. Yes. So that is what we are trying to, not does form part of this thing. And best estimate approach provides management solution to deal with over conservatism. Often it has been seen during operation that over conservatism is putting a constraint on the plant, which is again is not good. It tends to be good at times for safety also and for availability also, so or reliability also, you know. So those kind of situation, definitely this kind of canvas is going to help the plant, and operation decision can be taken. Now salient feature of operation, see, because PRA I have been discussing in introduction also I had discussed in dependency, that is second module I had discussed, and so here I have put a symbolic use of this fault tree, event tree, and stress strength diagram where structural uncertainties are captured. So what is there? Plant resources and approval. For PRA we have to, it is a very expensive exercise. So we have to mobilize resources and create a framework for PRA. And subject expertise should be available, project management approach should be there, review and appraisal, quality assurance. PRA also requires a quality assurance program. If quality assurance tags are not there with the PRA document or then the regulators will find it difficult to accept this study even for starting the review. So overall encompassing preliminary exercises are done whether the PRA study is meeting a quality, and then once it is done, then once the work start, plant walk down, realistic data and information. So all the experts have to go to the walk down, not once, twice, thrice, as and when you require, and data collection starts. So plant specific data collection is the best thing it can happen to any PRA model. If we are doing the generic data in our PRA, then probably uncertainties in our predictions will be higher, but it is understandable because the plant was in design stage. But as the plant start operating, especially in the beginning, maximum effort should be put for updating the PRA model with the plant specific data. Identification of initiating events, yes, that is there. Maybe in operating state you might find one or two additional events, that is should not be surprising. System analysis, and then finally consideration of special area. I have written here human factor, common cause failure. These are the gray areas, and it has to excel because they carry larger uncertainty. The common cause failure also our understanding is by empirical formulation. Actually, basically physics of failure study should resolve this issue. Simulators are doing very well now, because during training, if the facility doesn't allow the degree of freedom is limited, simulators allow infinite degree of freedom for experimenting or simulating any session for better understanding and evaluation. Uncertainty and sensitivity analysis, yes, it is one of the I would say gift of PRA to even deterministic also. Results of the analysis. Documentation is very important and periodic updates are very important. Regulatory compliance, unless until regulator approves the study, it doesn't become part of the plant document. And then finally, developing application. Every application will require a regulatory approval. So, regulatory body has the final say on how the plant should be operated and how PRA result should be interpreted, whether any new element or surprising element is there. So that makes the whole process, because basically 3-tier review system is there. One is the analyst who is doing it, then inside the plant there is one reviewer, then another reviewer is sitting somewhere who is the expert, and then finally it is the regulator. So 3-tier review always help. Then significance of randomness in complex engineering system we have discussed. Quantum mechanics we have touched. It is basically to make a statement that randomness is part and parcel. You can start from nano to mega level. It will be there and you have to handle it. Role of PRA is that's how the role PRA has important role. Deterministic interface. How PRA and deterministic, they are having an interface and give and take and making it more holistic, that we have management aspect of the PRA. How to start the project, how results are obtained, how it is interpreted, what are the how to handle subjectivity. So with this, the lecture on deterministic analysis is over, and now in the next lecture, probabilistic analysis is over. So we have covered deterministic and probabilistic both. In the next lecture, that is week 3's last lecture, we will be discussing special aspects of risk-based engineering.